So in the second part here, we're going to begin our internal load evaluation, which we use the method of joints. And as I said before, and I'll do it here, I typically start with that pinned joint. Sometimes there's options. Other times there's only one joint that you would be able to get like enough known forces and loads that you can solve it. So we're going to start by trying the pin, and we'll see if we can't get a couple of these members' internal loads determined. So method of joints, we say, there we go. What we have to do is look at just a free body diagram of the joint. So for example, maybe I'll draw it right here. We've got point B, and from our original free body diagram, we had, let's see, we assumed that. So I believe our R, B, and the X is pointed to the right, and we found that to be 50. We also have the reaction force in the Y. Found that to be 50. These are all pounds, by the way. And what else? So that's our reaction forces. Now we need to look at the forces of each member. So now we have member AB, and as always, when we look at the internal force of a member of a truss, we assume the member to be in tension, and when you do that, what that means is you point the arrow representing the vector of that internal force, you point the arrow away from the joint to represent tension. So that would be member AB, and that's all of AB. There's no AB in the X and Y, it's just everything is AB, it's all in the Y direction. But at this point we have BC left, and BC is at an angle. In fact, it's 45 degrees. We know 45 degrees in this case because, as you can see, we've got 3 feet vertical, 3 feet horizontal, so 45 degrees. There's 2 ways to write the free body diagram. I'll draw the first one as your traditional. Here's your vector, that is vector BC. But I don't know, to me that's not super helpful, especially because the first thing we're going to do after the free body diagram is we're going to create our equations, some of the forces in the X and Y. And if we have a vector that is not exactly X and Y, it's not really that helpful. So I'm going to redraw this and say X is 50. And then we have AB, remember AB, that's all AB. Now, vector BC, this is where I said it's going to be more useful. So what I'm going to do is I'm going to redraw BC in its components. So this is BC in the Y, and because our vector goes down and right, I'm going to draw exactly that. I'm going to draw a vector down and vector right. That's BC in the X. Now we can look at this in a larger picture and see that we can find summation of the forces. Let's start with summation. Well, actually, let's see. What can we do here? How do we know, do we do X first or Y first? If we look at our X forces, let's see, we have 2 forces, right? We have RBX and BCX, and that's it. We know one of them, we don't know the other. That means if I write an equation for the summation, we will be able to solve it. If we look at the sum of the forces in the Y, we have RB in the Y, which we know, but we also have AB, which is not known, and we have BCY, which is not known. If we try to do forces summation in the Y, we have too many unknowns. So just based on that preliminary assessment, I'm going to say the sum of the forces in the X is 0. So our X value, so we have, whoop, there we go. So negative RBX plus BX. as 0. So B, C in the X is equal to the reaction of B in the X, which we know was 50 pounds. So BC in the X is pointed the right direction. We assumed correctly, but that's not as helpful. We need to know BC itself. So let's draw our picture. Over here. No, over here. I'm going to draw. So we have 45 degrees here, and our vectors. So the vector BC is here, right? This is BC. We have our down, we have our right. Here's BC and the Y, and so what's happening is we need to figure out. We know BC X is 50. Turns out then if that's 45 degrees, we'll eventually say, oh yeah, that's 52. But we just want to find BC for now, and when we do that, we know that. Let's see, so sine of 45 degrees is our 50 over BC. So BC, we want to know BC. BC is equal to 50 over sine 45. Which, if you get out that handy dandy calculator, we've got 50 divided by sine 45. Make sure you're in degree mode. 50 over sine of 45 is 70.7. So 70.7 pounds. So BC is now solved, and that is 70.7 pounds, and that is in tension because we solved the whole thing. We got BC, we did not get a negative number, so therefore we assumed correctly, so tension. I'm gonna even, just like we did external forces, so now we have AB, BC, and AC. So internal loads on these three members, we just found vector BC to be 70.7 pounds. And we'll box it in. Eventually we'll have them all filled in. And now we've got enough information that we can say some of the forces in the Y are 0. And the forces in the Y direction are, well, let's see, BC, that's that, do I have it that way? If you look at our free body diagram, vertically we have a positive R, BY. We have AB, remember AB, and we also have BC in the Y direction. So 0 is RBY, so 50, minus AB minus BC in the Y direction, which is 50. Nope, yeah, 50 from over here in the triangle. So 50 minus AB minus 50 is 0, so 0 minus AB equals 0. So AB is 0. Why did I lose my pen? That's weird. Not sure what just happened. Somehow I think I lost. Yeah, lost a bunch of work. Great. All right. Well, where we were was we said that the sum of the forces is 0, but 0 was equal to the RBY, which was 50, minus our AB minus our BCY, which was 50. So what we found out was that AB, so 50 minus 50 is 0, so AB equals 0. So AB is a zero force member, we call him. Now, Member AC is not solvable from joint B. You can only solve members and their internal forces by doing the free body diagram and the method of joints from a joint that your member you're trying to solve is attached to. I think I can probably get this figured out. If I pause and I'll get set up, and we'll do method joints at joint A and be able to solve that last member AC. All right, so bam, here we are. Next page, method of joints at joint A. Sorry, I should label this joint A. The free body diagram looks like the reaction force at A and the X. Remember, there's no reaction in the Y. AC, we are assuming in tension. We always assume in tension. Even though I can tell you right now it's going to be compression, I still write it out as a tension. So that points away from the center. The AB, remember AB we just solved, that was 0. So I don't care what direction you point the arrow. But also AC is perfectly in the X direction. So remember AB wouldn't have any effect on it anyway. If we look at this as the sum of the forces, hopefully it's obvious to you, we have to choose in the X. Those equal 0. Right now, we have RAX positive plus member AC positive. That is 50 plus AC is 0. So now we're saying AC equals negative 50 pounds, which really means AC is equal to 50 pounds compression. So I am going to take and scroll back up here and call that 50 pounds. That was in compression. 0 pounds, you don't put a compression or tension. BC, we did assume in tension. I forgot. This is my fault. I forgot to put the T in parentheses. So we have all of our, you know you're done when you've done the external loads and got the reaction forces, and then you've gone through and figured out the internal load of all of your truss members. At this point, what you typically end up doing is you'd have like one page where you have your your external forces and internal forces listed, as well as you would take time and redraw this diagram and include the 0 pounds, 50 pounds compression, and 70.7 in tension. You would also redraw it, with RAX equal to 50, and then RBX 50, and this one here. Oh, screwed that up. Sorry, that is not RBX, that is RBY. Like that. So you would end up with 2 boxes, your external loads, your internal loads, and then a final fully filled out free body diagram. But that is 2.1.7 question 4.